Welcome to another exciting video. I know, you're rolling your eyes, I get that. We're going to talk about enthalpy. Okay, for our purposes, we're going to consider enthalpy to be the same as heat energy, only because all of this stuff that we're doing is at constant pressure. So we can make this assumption for constant pressure, which allows us to use algebra, not calculus. Good for you. It's actually more entertaining in calculus, but I get it. I'm a geek. All right, here we go. One thing you need to know about enthalpy is it is a state function, and I don't mean dinner with the president. I know that was bad. Anyway, the state function means the path does not matter. It only matters start and finish. So if I were to push this car up the garage, I'm going to feel like I'm spending a lot of energy. True that. The energy change is definitely different than if I run the car up the elevator. The point is, enthalpy only cares about your initial and final positions. In this case, that would be the elevation gained by the car. It is exactly the same, no matter the path the car takes. The change in enthalpy is easy to calculate, well, somewhat. There's three different ways to calculate it. The one way you can calculate it is to look at the difference between the products and the reactants. But what you need to know about a state function, the path doesn't matter. If I go from reactant A to product B in one step, or if I go from reactant A to an intermediate to product B, the change in enthalpy from beginning to end, exactly the same. It doesn't matter the path. There's three ways to calculate enthalpy, products minus reactants, and we'll look more in detail at that soon. We could use Hess's law. We did that in Gen Chem, and we did this in Gen Chem, which basically boils down to a dimensional analysis problem. Because for this reaction, for every 1 mole of propane, the amount of enthalpy, heat energy that's released, is that number that I just put up on the screen. So basically the plan is we're going to need to convert from 5 grams of propane to kilojoules to find out the total amount of heat. Well, looking at this problem, we're going to start with grams, convert it to moles, and convert it to kilojoules. So we take 5 grams of propane, converting that to moles using the molar mass, then using the propane value that we got. See, the 1 mole of propane I just put there came from the balanced equation. The coefficient in front of propane is 1. So for every 1 mole of propane, that's the amount of heat energy that is released for this chemical reaction. And plugging it into your handy-dandy calculator, there's the amount of kilojoules produced by this chemical reaction for 5 grams of propane. From the previous problem, you should have guessed that you absolutely do need a balanced chemical equation for these to work. I encourage you to pause the video, see if you can try the problem on your own before I actually show you how to do it. But, you know, whatever. The amount of energy you put into this is entirely up to you. That said, I'm going to convert from grams of methane to moles of methane to kilojoules. Starting off with grams of methane, using the molar mass, to 1 mole. Then 1 mole contains negative 890 kilojoules. Now that negative sign, I know you're probably going, it's not in the problem. That's true. The key word here is released. And when energy is released as heat, released, it's leaving the system. That's a negative sign. It's an exothermic reaction. You need the negative sign. Plugging it into your handy-dandy calculator, booyah, there's your answer. Yes, I know it's not exactly what the calculator said, but I was paying attention to significant figures. Okay, so you should be able to do those homework problems now. Calorimetry. Well, you know me, I prefer to call it joulerimetry since we don't use calories in our calculations because that's the stupid English system. Remember, we use a joule, but we're stuck with the name calorimetry. Well, if I did a chemical reaction inside a calorimeter, then the absolute value of heat in that chemical reaction would be exactly the same as the heat in the water. And since, you know, we have a lot of information about the water, we can figure out the other half of this equation. Just to remind you about the equation, your book uses SM delta T, where S is the specific heat capacity of the substance. That's a number you look up for everything except water, because that one I expect you to know. But it's unique for each substance. And then M is the mass, and delta T is the change in temperature. I prefer to use the equation Q equals MCAT. You should remember that. For this problem, you could do a bunch of calculations and come up with an answer, but since the amount of water that's hot and the amount of water that's cold is exactly the same quantity, the same mass, then your final temperature will be exactly in the middle. It's like, washing dishes and you have cold water and you want to raise the temperature. You add hotter water than the water you actually need, the temperature of the water that you actually need. I'm sure that made perfect sense. I hope it did. Anyway. This problem, the average number, the middle number, the median number between 90 and 10 is 50 degrees Celsius. This problem is just a little more complicated because we have different masses of water, so you can't actually just sort of guesstimate it. You could guesstimate it because you have a lot more water at a colder temperature than you do of the hot water. So I guess that it's going to be colder than the 90. I'd say it's closer to 25, 30 degrees Celsius. It's going to be closer to the colder water temperature because you have more cold water. But if we were to do the math, here we go. I know Q equals MCAT, and I know delta T is the final minus initial temperature. In a perfect system, the amount of heat energy lost or gained by one is directly equal to the amount of heat energy lost or gained by the other. The magnitude of Q should be the same. The difference is the sign, because one gains heat energy, one loses heat energy. Well, since Q equals MCAT and T equals T sub F minus T sub I can make this assumption. Now I'm going to plug in my numbers. It doesn't matter which is 1 or which is 2, just so long as you stay consistent on one side or the other. But please notice, I can cancel out the C's. Because we're dealing with water, the value of C on both sides of this equation is identical, so those cancel out. That's a nice start. Plugging the rest of our numbers in, then solving for T sub F, 23 degrees Celsius. Okay, so this is like a lab we did last year. We took a piece of hot metal and we put it into cooler water and had to come up with the specific heat of the metal. But in this case, I've given you all the information you need except the final temperature of the system. And both the water and the iron ball will reach the exact same final temperature. Read through this, make a guess at what you think the final temperature of the water will be. And then we're going to calculate it using the actual math. Using the same equation we did before when we had the hot water and cold water example, now same one, but now we got to leave the C's in because the specific heats of both of them are different. Plugging all of your numbers in, solving for F, final temperature 18 degrees Celsius. I know this problem has a lot of words in it, but don't freak out. It's not that hard of a problem. So, of course, we need a balanced chemical equation, and then I write down the information that was given. The first thing I'm going to do is figure out how many grams of solution I have, and because the density of the solution is the same as the density of water, then I know that if I have 2,000 milliliters, I have 2,000 grams of my solution. Now, for the amount of heat energy, I simply put in the grams. The previous problem said that the specific heat was the same as that of water times the temperature change. And there you have the answer. The energy of the solution is 2.31 times 10 to the 5th joules. Again, another problem with a whole big bunch of words. Well, here's how you attack this one. The heat of the calorimeter is that. And so just multiplying it by the temperature change, you'll get the amount of kilojoules in this for this calorimeter. Then we simply divide it by the grammage used, and that's the heat energy from burning that much methane in that calorimeter. And basically you're going to do the same thing then with hydrogen. And then per gram. It asks you to compare those two. So what this means is hydrogen combusts 2.55 times more than methane. Those problems are your homework.